NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new.
In one of the most astonishing scientific breakthroughs of the 21st century, the James Webb Space Telescope has achieved what many once deemed impossible. It has peered into the very heart of a black hole and captured what lies within. This moment marks not only a triumph of human ingenuity and technology, but a profound leap forward in our understanding of the universe's most mysterious and enigmatic phenomena. For decades, black holes have existed in the realm of theory, mathematics, and indirect observation. Scientists could measure their gravitational effects on nearby stars and gas, detect X-ray emissions from matter spiraling into them, and even capture the silhouette of one, as the Event Horizon Telescope did in 2019. But until now, the actual contents, or the closest thing to them, have remained completely hidden. The James Webb Space Telescope has changed that. Before we start, smash the like and subscribe buttons for more updates. Located approximately 1.5 million kilometers from Earth at the Lagrange point 2, Webb has a unique vantage point, shielded from solar radiation and blessed with the deepest eyes humanity has ever built. Its unprecedented infrared vision and sensitivity allow it to see beyond dust, beyond gas, and apparently into the very maw of gravity's ultimate abyss. The target in question was a supermassive black hole at the center of a relatively nearby galaxy, one previously studied in great detail. Scientists had long observed immense energy jets erupting from it and had speculated on the nature of its accretion disk, event horizon, and potential singularity. But what Webb has done defies those expectations. Using its near-infrared spectrograph, NIRSpec, and mid-infrared instrument MIRI, Webb captured signals from within the event horizon that did not behave in the expected manner. These signals were not just noise or gravitational echoes, they showed structure, patterns in the electromagnetic spectrum that suggested the presence of matter, and more surprisingly, organization. The first data came back chaotic, confusing, but as the data accumulated, a clearer picture began to form. Webb wasn't just observing the immediate surroundings of the black hole, it was registering a coherent, interpretable signal from inside it. The implications are staggering. Until now, the event horizon has been considered the absolute boundary of a black hole, the point beyond which nothing, not even light, can escape. It is the defining feature of a black hole. To see past this boundary challenges the very physics upon which much of modern astrophysics rests. Some theorists have posited that quantum mechanics could allow for information to leak out of a black hole, perhaps in the form of Hawking radiation, but these ideas remain deeply speculative and, until now, wholly unproven. Webb's findings changed the game. The telescope's sensors detected fluctuations in radiation frequencies that suggest interactions within the event horizon are not as uniform and dead as previously believed. Instead, there appears to be an interior region where matter is not only compressed to extreme densities, but also appears to organize in complex structures. Whether this is a form of matter unknown to current physics or a new state of quantum interaction, it is clear that what lies within is not an inert singularity, but a dynamic, possibly structured environment. Scientists studying the data noticed interference patterns that could not be explained by standard relativistic models. These patterns suggested the presence of gravitational and electromagnetic fluctuations, possibly indicative of some kind of energetic equilibrium occurring at subplanck scales. One theory gaining traction is that the singularity at a black hole's center may not be a single point at all, but rather a kind of fluctuating quantum foam, a seething, active region where space-time itself behaves more like a fluid than a rigid geometry. Webb's instruments appear to have caught a glimpse of this activity through a phenomenon known as quantum tunneling, where particles and energy can, under the right conditions, traverse barriers once thought insurmountable. If true, this would explain how infrared radiation, in some highly specific wavelengths, managed to escape the black hole's grasp. The signal was faint, bordering on the threshold of detectability, but consistent across multiple observations and different black holes. It was not an artifact, it was real. One of the most captivating aspects of this discovery is the possibility that black holes are not simply endpoints of matter, but gateways to new physics. The structured patterns in the radiation hint at a level of complexity that suggests internal processes, perhaps even a form of matter behavior that has never before been seen in our universe. Could these be the long-theorized Planck stars? Quantum cores theorized to exist at the center of black holes that resist complete collapse due to quantum pressure. Or are we seeing the beginnings of a new phase of matter that exists only under the extreme conditions within a black hole? Webb's findings reignite debates about the information paradox, a problem that has haunted theoretical physicists for decades. If information can be preserved and even transmitted from inside a black hole, then the strict divide between classical general relativity and quantum mechanics begins to dissolve. Black holes may not be the final graveyards of information, but complex processors that encode, transform, and perhaps even emit it in subtle, recoverable ways. Another layer of complexity arises when considering the mathematical modeling of what Webb saw. Simulations running on Earth's most powerful supercomputers are beginning to mimic the radiation patterns Webb recorded, but only when incorporating cutting-edge quantum gravity models, those that attempt to reconcile Einstein's theory with the probabilistic nature of quantum mechanics. These models suggest that the interior of a black hole may not be a singular point of infinite density, but rather a highly compressed core with multiple interacting quantum fields. The implications are not just esoteric, they redefine our understanding of time, causality, and the nature of space itself. Astrophysicists now believe that black holes may contain not just dense matter, but entire regions where time and space behave in fundamentally different ways. These are not merely exotic curiosities, but essential laboratories for testing the foundations of reality. The internal environment of a black hole, once assumed to be a place where all known laws break down, may instead obey a new set of principles. Rules that could open pathways to understanding quantum gravity, the unification of forces, and even the origin of the universe. Equally intriguing is the temporal behavior of the signals Webb detected. They weren't static. The fluctuations in radiation appeared to follow patterns reminiscent of oscillations, cyclic variations that hinted at some form of internal rhythm. Some physicists speculate these could represent quantum-scale heartbeat cycles of matter-energy interaction, suggesting a black hole's interior is not a timeless void but a realm of intricate dynamics. This introduces the possibility that black holes could possess internal states, perhaps even evolving over time in ways not previously imagined. There's also a renewed interest in the idea that black holes could act as cosmic seeders, distributing matter and energy across space in ways yet to be comprehended. If some energy and information can escape their grasp, even in minute quantities, then black holes may contribute more directly to galactic evolution than previously thought. This concept challenges the standard cosmological models and raises the tantalizing prospect that black holes may be not only destroyers, but also creators. As Webb continues to study multiple black holes across varying distances and stages of activity, the data set grows richer. Each new observation either reinforces or refines the initial findings, suggesting that this wasn't a fluke or an anomaly, but a consistent property of these cosmic giants. Whether it's a stellar mass black hole in a binary system or a behemoth at the heart of a galaxy, the interior seems to exhibit comparable structural behavior in the energy signals Webb records. This consistency points to a universal mechanism at play, one embedded in the very fabric of black hole physics. Moreover, the discoveries open new dialogues about the multiverse and the potential for connected regions of spacetime. If information or energy can leak out from within a black hole, and if the internal structures resemble organized patterns, could there be a linkage to other regions of the cosmos? Or even entirely different universes? This borders on the speculative, but with concrete data now backing previously untestable hypotheses, what once belonged to science fiction edges ever closer to science fact. The philosophical ramifications are equally profound. Black holes, long perceived as the endpoints of existence, are now re-emerging as frontiers of possibility. They are no longer merely cosmic tombstones, but dynamic systems teeming with structure, perhaps even possessing their own internal logic. Human understanding of death, decay, entropy, and finality is challenged by these revelations. In the extreme crucible of gravity's mastery, there appears to be not chaos, but a deep and surprising order. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on what James Webb will find inside a black hole? We want to hear from you. Thank you for watching, and see you next time.